project on the golden spiral and fractals. So the golden spiral. What's doing? It's not working. Wait. Okay. Sorry. Okay. So the golden spiral is a logarithmic spiral, and the logarithmic spiral is actually like a spiral that increases by a steady rate. And the way they determine this is from any point on it. If you draw a tangent to the spiral, and then you connect it to the center of the spiral, it'll always form the same angle wherever you put your point. So the golden spiral is special because it increases by a rate of approximately 1.618, or 5, which is represented by this Greek number, or this Greek letter here. So the way that most people create the golden spiral is they start with a rectangle with a ratio of the golden, or of 5, which is a side of 1 to 1.618. And then the special properties about this thing that make it cool to create a spiral with is that when you divide it into a square and another rectangle, the other rectangle also has a proportion of 1 to 1.618. And so you can keep doing that, and you can do it indefinitely. So then to actually create the spiral, you connect inside of each square, you make a quarter arc, and so you do that, and then you get your golden spiral. So I created this one in Sketchpad with a golden rectangle and then the quarter arcs. Another common thing is the Fibonacci spiral, which a lot of people think is the exact same thing as the golden spiral, but in actuality they're different. They're created a different way, and they actually aren't quite the same spiral. So the Fibonacci spiral actually starts with just a little square, and then another one identical to the first one is placed next to it. And when a third one is added, the sides of this rectangle become 1 to 1.5, which isn't actually the golden ratio, making it not like an actual spiral. But as it goes, so 1 to 1.5. But as it goes out, the ratio of the sides gets closer to the golden spiral's ratio, making it pretty close to the golden spiral, but still it's not exactly the golden spiral. So I also created this one in Sketchpad. Also in Sketchpad, what I did first was I created the ratio of 5. There's like a lot of different ways to create this, but the way that I did is I inscribed an equilateral triangle into a circle, and then I created the midpoints of two sides, and then I connected the midpoints and extended it out to the outside of the circle, and the ratio of that whole segment to the ratio of just the part inside of the equilateral triangle is actually the ratio of 5. So I thought that was pretty cool. And then I also created the golden rectangle and the golden spiral inside of it. And the way that I did this was I started with a square. And I just researched this, and this is what it said to do. So the opposite sides, I created a midpoint to, and then I connected those points to the segment. And from the bottom midpoint to the top corner, I connected them with a diagonal. And then I extended the bottom line, and I made a circle with the radius, the diagonal that I created, and the center, the bottom midpoint. So then when I created a perpendicular from the point where the circle intersected the bottom part, and then I extended the top line, I actually had a golden spiral. Now I wasn't really quite convinced that this was actually a golden rectangle, because like sometimes, like I had tried a few other ones that just didn't look right. So I kind of came up with like a way to like prove, but not really prove, but like show that it is actually one. So I started with the midpoint and the diagonal there. And then I called the bottom half part right there x. So then the whole side of the square I knew had to be 2x. And then since it's a square, the bottom part was a right angle. So with Pythagorean theorem, I figured out that the diagonal line there is x radical 5. And then I was able to, since I created this with a circle, I know that all radii in a circle are congruent. I got that the bottom part there is also x radical 5. And also, because that original part was x and the midpoint makes them both congruent, I knew that that part had to be x. And therefore, when you added it to that part, it was x plus x radical 5. So now I just knew that 2x to x plus x radical 5 had to be 1 to 1.618. And so I made 2x 1, which made x 1/2, And then I did, so x plus x radical 5, I substituted in the x, and then I got 1 over 2 plus 1 over 2 radical 5, which is 1 plus radical 5 over 2. And if you do that out on a calculator, you actually get 5. So it worked, and I made a golden rectangle. So there was my spiral. I just connected the squares with quarter arcs. And then I made the Fibonacci spiral too, but that one was a lot easier because it was just squares. Okay, so there's another part in here, like the whole thing of the golden spiral in nature. Like a lot of people think that the golden spiral is found in nature, because like you can see spirals and stuff. Like an example of this that most people think is like a really good one is the Nautilus shell. And as you can see, there's a nice logarithmic spiral in there. But when you put over a golden spiral, you actually see that it doesn't match up. Because even though it is an equiangular spiral, and it's a pretty nice, perfect spiral, it doesn't increase by a rate of the golden ratio. And like most of these spirals don't. If there was one that did, it would be like a rare one, and it's not common to find the golden spiral in nature. Like, it's not a thing like all over. So here's a golden spiral that is on like, it's an actual like perfect logarithmic spiral that someone constructed on a graph. So now if I take, here's the normal one that most people think like you do, where you construct it with the squares. And when I put them over each other, you can see that they don't actually match up. And it's not just like my computer like not being like perfect. They actually aren't exact. So the one where you make the golden rectangle and then divide it, because you're just putting inside each square a quarter arc, it's not exactly the golden spiral, but it's just close enough that most people have come to regard it as the like actual golden spiral, even though it's not a precise logarithmic spiral, but it's still close. So fractals. I also did a part on fractals. And so a fractal is like a shape that like is infinitely repeating itself. So it kind of like, each shape as it goes, like it follows a certain pattern, and each shape gets like smaller, and it's kind of like another, like it's similar to the original shape, or at least like really close to being similar. These fractals, they're never like random, or they're never like, random, but they can be like kind of like irregular and complex, but they always do have some pattern, and the like other parts are always similar to the original one, or at least pretty close to being similar. So one of the most famous ones is called the Koch snowflake, and this is a colorified version of it. So it's actually like, it's really simple to create. You just start with an equilateral triangle, and then from one side of it, like here's one side, and then you split it into 3 parts, and just put an equilateral triangle over the middle part, and then you take out the bottom one, and if you do that on all sides, you get kind of like a star-like looking thing. And then from each side of the star, kind of, if you come and you take and do the same thing to each one of those, it also, like, it gets bigger and cooler, and it looks more like a snowflake. So this is a really cool fractal because it has, like, an infinite perimeter. And so it, like, because you know it can keep going on like that forever, because fractals go on indefinitely, or until, like, you personally like, stop them. So, however, with this infinite perimeter, it does have a finite area, because if you inscribe that original triangle into a circle, the area of it can never exceed that original circle. So it's an infinite perimeter with a finite area, which I think is pretty awesome. So, go back. Okay. So let's go back. All right. So another thing I did is this is the Sierpinski triangle. I think that's how you pronounce it. It starts with an equilateral triangle, and then from the midpoints of each side, you connect them and make another triangle in the middle. And so it gives you 4 triangles, 3 on the outside and 1 on the inside. Now from only the outside triangles, you also connect the midpoints and like make another triangle inside of there. Then you do that, like you can keep going on indefinitely, and it creates like a really cool like pattern. This also can be like 3D, like as you see here. You can do it with like 3D stuff too, and I think it looks a lot cooler when it's in 3D and stuff. So fractals like aren't just computer generated stuff, they're also like in real life too. Like unlike the golden spiral, fractals actually are in nature. They may not be perfect ones, but they are still there. Like here's a fern, and like the same basic leaf design is copied over like along the stem, and each one is kind of like the original. It's not exact, but it's still a fractal because it's pretty close to the original one. This also is found in like leaves, like how they branch off and stuff, and like trees and crystals and snowflakes too. So in Sketchpad, I wanted to create, like I had done the golden spiral and stuff, so I wanted to create fractals. And I found like some really cool things. Like I found iterations where you can actually like go in and like go plus plus, and it like goes farther into the fractal. You could keep going on like that into infinity, where you like specify a certain way for it, like for your geometric shape or whatever to like go, like the stars I have going up there. I didn't actually create this one, but so I kind of created this in Sketchpad. However, I couldn't figure out how to do it with like iterations, just because like, I don't know, there's so many things it's doing. Like mine's going in the middle, and then it's going up, and like these stars right here. I took away all the lines too, so it's just the beautiful stars going up. So yeah, I wanted to be able to create it with the like iterations, so it goes forever. As you can see, this one like kind of stops up there, but I couldn't. I figured out how to use iterations, and I thought it was really cool though, and it was like awesome to be able to use iterations. If you know what they are, I didn't quite understand them either. So these two things I think are kind of related in this like hair spiral. Miss Verdino actually showed it to me, and it's kind of what like got me interested in like both of these projects. So it's this cool spiral here that kind of looks like a fractal golden spiral. Like if you kind of see what I mean, like it's kind of goldeny and then it spins. So it starts with a rectangle, and this rectangle is in a proportion of 1 to 1.325. So if you divide it and you create another rectangle, like the blue one, that's in a ratio of 1 to 1.325, and then this other one over here, this orange one, from the leftover area, you could create another one that's also 1 to 1.325. And then I'm pretty sure what's left over is a square, but that like there weren't very many articles on it, and nowhere specified that this was actually a square. So I wasn't quite sure about that. But however, to create the hair spiral, you take each one of these now, and then you divide it again like we had before, and you do to each one of the little one, like the little orange and blue ones we created now, you can do that again and again and again, and then eventually you'll end up with something like this. And from here, they connected the outsides with like curves or arcs to create like this cool spirally thing. And then they did that kind of again with all the leftover boxes, and they got this. And then that big ugly arc there, they just deleted that, and you have the hair spiral. So that's the hair spiral. And here's the, it's not working. It's a dog at fractals, like it goes up. It's like, it's cool. It's not working.
Terrifying.
See